Welcome back, Grade 9 students of St. Paul American School Clark, to today's Explainer. I am absolutely thrilled you're tuning in because what we've got lined up today is basically your ultimate strategic playbook to totally ace your upcoming geometry performance task. We're zeroing in entirely on Unit 2, Lesson 7, the Transformation Construction Performance Task. So if you're looking to build a flawless geometric transformation and snag those top marks, you're in the exact right place. Let's get to it. Okay, let's dive right into this core idea. We aren't just looking for the right drawing. We're looking for the precise mathematical reasoning. You know, in a standard performance task, doing the construction, actually making the shape appear on your screen, well, that's really only half the battle. Defending that construction using precise mathematical vocabulary, that's what actually earns you full credit. You literally have to prove that you know exactly why your drawing is correct. Here's our structured roadmap for the explainer today. Number 1, the performance task. 2, digital tools and vocabulary. 3, building the transformation. 4, checking for misconceptions. 5, a quick knowledge check. And 6, our final review. Section 1, the performance task, your student-ready challenge. All right, here is the specific prompt you're going to face. You're required to rotate a polygon exactly 90 degrees counterclockwise around a specific center point on a coordinate plane. And this is absolutely crucial. You must use geometry software. This isn't just a quick freehand sketch on grid paper, right? You can't just click and drag a shape around until it kind of looks right to your eye. Instead, you have to purposefully select the software's tools, meticulously label your starting shape, which we call the pre-image, and your final shape, the image. Plus, the whole shebang requires you to provide a written mathematical explanation proving that the measurements of your shape were completely preserved during the rotation. Section 2, digital tools and vocabulary. Precision is mandatory. Now, to build a truly rock-solid mathematical defense, formal definitions are absolutely your best weapon. Take the definition of an angle, for instance, the union of two rays or directed line segments that share a common endpoint called the vertex. When you write out your mathematical explanation, using this exact kind of rigorous language proves that you understand that rigid motions, like rotations, keep these specific angle measurements exactly the same from the pre-image straight through to the image. Of course, to actually physically build this mathematically sound rigid motion, you're going to be relying on digital tools, most likely within an environment like GeoGebra. So you really need to master 3 basic tools. First up, the point tool. This is how you'll define your polygon's vertices and lock in your center of rotation. Second, the segment or polygon tool. This is what you use to construct the shape itself. And third, the line tool. That one is incredibly helpful if you need to establish any axes or visual guidelines. Knowing exactly where these tools are on your screen and knowing exactly what they do, well, that's foundational to passing this task. Section 3, building the transformation, step-by-step execution. And this brilliantly illustrates exactly how to map out those software clicks. These 4 sequential steps basically form the core of your defensible solution. Honestly, I'd write these down. First, you'll use your polygon tool to plot the initial shape, your pre-image. Second, you've got to plot a distinct separate point to serve as your center of rotation. Third, you apply the software's rotation tool, select your shape, select your center point, and then specify exactly 90 degrees counterclockwise. And fourth, please do not skip this, you must carefully label that resulting final figure, the image. Now, to back up step 3 in your written explanation, you'll want to use this formal definition provided by mathematical research. A rotation is turning a pre-image around a center, where the distance from the center to any point on the image stays the same. In fact, every single point lies on an invisible circle around that center point. When you actually type out your reasoning, explicitly stating that the distance from the center to any given point remained identical, well, that proves you didn't just let the software do the work for you. It shows you actually understand the geometry running behind the software. Section 4, checking for misconceptions, avoiding pitfalls. Now, what's really interesting about this concept is a very specific common error that educational researchers often note, confusing a rotation with a reflection. While a 180-degree rotation and a reflection might look somewhat similar at a quick first glance, they are entirely different geometric transformations. A rotation requires a center point and an angle. And remember, by mathematical convention, a positive angle means counterclockwise. A reflection, on the flip side, requires a central line of reflection to create a mirror image. So listen closely. Do not use the word reflection or flip anywhere in your defense for this task. You are performing a rotation for sure.
Section 5. Quick knowledge check. Test your readiness.
Let's pause for a second. Think back to step 4 of our execution process. Here's a quick question to see where we're at. When your original polygon moves, how must vertex A be labeled on its new location in the image? Take a second to think about it. Go ahead and say it out loud if you need to. If you said A prime, you hit the nail right on the head. You absolutely must use that little apostrophe mark. Vertex A becomes A prime, vertex B becomes B prime, and so on. Proper prime notation isn't just a friendly suggestion, it's the universal language of geometric transformations. It is literally mandatory for full credit on your performance task because it mathematically communicates that this new point is the direct output of the original point.
Section 6, Final Review, your strategic playbook.
So the crucial point is really bringing all this together. Here's your core concepts recap for the transformation construction performance task. First, purposefully use your precise digital tools. You need to know the clear difference between your point, polygon, and line tools. Second, execute that perfect 4-step rotation sequence. Draw the pre-image, plot the center point, apply the rotation tool at 90 degrees counterclockwise, and label everything with prime notation. Third, justify your work. Prove it's a rigid motion by leaning on formal vocabulary like the definitions of an angle and a rotation. And finally, maintain total clarity. Understand the distinct difference between rotations and reflections so your written defense is absolutely flawless.
Which leaves us with one final thought. You know exactly how to make the drawing, and now you have the precise language required to actually prove it. So grade 9, I'll leave you with this. Are you ready to mathematically defend your geometric reasoning? I know you are. Good luck on your performance task, and keep learning.